In this video, we're going to learn a few more derivative rules, specifically how to take the derivatives of logarithmic functions, exponential functions, and inverse trigonometric functions. And of course, all of these rules will also be all mixed up with our product rule, quotient rule, chain rule, all of that. We just keep adding on to our list of rules. Let's start with our logarithmic functions. In particular, let's start with the natural log. The derivative of natural log of x is equal to 1 over x. So this rule, I would honestly suggest that you memorize it. It comes up quite a bit, and out of all of the logarithms, we use the natural logarithm the most in calculus. So this is by far the most important logarithm differentiation rule. Now, if I were to want to find the derivative of a logarithm with a different base, there is a formula you can memorize for it, but you can also just use the change of base formula and you would end up with the same answer. So let's look at log base b of x, so any base b. Recall our change of base formula from back when you took pre-calculus. Log base b of x is equal to the natural log of x divided by the natural log of b. So then I can find the derivative of a log of any base by changing it to natural logs and using my natural log formula. So we have the derivative of a log with base b of x is equal to the derivative of natural log of x over natural log of b. And that natural log of b is just a constant. So this is equal to 1 over the natural log of b times the derivative of natural log of x, which is derivative of natural log of x is 1 over x, and we have a natural log of b in the denominator from multiplying by this 1 over natural log of b. So the derivative of log base b of x is 1 over x natural log of b, and you can memorize that one, or again, you can always just use the change of base formula, and then you only have to memorize derivative of natural log is 1 over x. So let's do some examples using our new rule. Let's do the derivative with respect to x of the natural log of x squared plus 1. This is going to be a chain rule problem. My outside function is a natural log. The inside function is x squared plus 1. So the derivative of natural log of x squared plus 1, we start with doing the derivative of the outside function. The derivative of natural log of x is 1 over x. So the derivative of natural log of something, we're going to have a 1 over that something. And then I need to multiply by the derivative of the inside function, which derivative of x squared plus 1 just gets me 2x. So rewritten, this is 2x over x squared plus 1. So again, if you have a natural log of more than just x, you use your chain rule, and it becomes 1 over the stuff in the parentheses times the derivative of the stuff in the parentheses. All right, so that one wasn't too bad. Let me do another one just like that before we do a harder problem. Let's do a derivative of the natural log of 3x squared minus x. So again, this one's going to be a chain rule. I have to do 1 over the stuff in the parentheses times the derivative of the stuff in the parentheses. So when I take the derivative of this inside function, I need a power rule to get me a 6x. And then remember the derivative of x is 1. So when I simplify this, well, it doesn't really simplify, but I'm going to get 6x minus 1 over 3x squared minus x as my answer. All right. So now let's do a more complicated example. Let's find the derivative of the natural log of x squared times sine of x over a square root of 1 plus x. Now this looks terrifying, and I know that, because right now you're thinking, okay, well, it's going to be a chain rule. I have to do 1 over all of that stuff in the parentheses times the derivative of the stuff in the parentheses. But how would I do the derivative of the inside here? It's a quotient rule, but to do the derivative of the top, I need a product rule, and to do the derivative of the bottom, it's another chain rule. So do we really want to do this as a chain rule with a quotient rule and a product rule and another chain rule? That sounds pretty terrible. But this is going to be our inspiration for another technique that we're going to learn next. This is the way you deal with having a derivative of a log with a bunch of stuff inside of it. We have our logarithm properties that we were reminded of a few videos ago. Remember, when you have a log of a quotient, you can split it up as the difference of logs. Log of a product is the sum of the logs. And when you have a power inside of a logarithm, the power can come in front. So let's first rewrite this using our log properties, and then we'll take the derivative. So we're going to use our properties of logarithms. So I'm going to instead do the derivative of, well, this is log of a quotient, so this is natural log of the top minus natural log of the bottom. And I'm going to rewrite the one in the bottom with a 1/2 power instead of a square root. And now I can simplify even more with log properties. We will be taking the derivative of a natural log of x squared plus a natural log of sine x minus a 1/2 natural log of 1 plus x. And then there's still even one more simplification I can do. This 2 can come down in the front. So rewriting again with my log properties, we will be taking the derivative of 2 natural log of x plus natural log of sine x minus 1/2 natural log of 1 plus x. And now we can take our derivatives. This guy is just straight up just the derivative of natural log of x. That's not bad. This one's going to be a chain rule, and so is that one, but they're not as bad as what we had before. So now when I actually take the derivative, this 2 is going to stay, and the derivative of natural log of x is 1 over x. Now for this guy, we need to do a chain rule. It's going to be 1 over the stuff in the parentheses times the derivative of the stuff in the parentheses. Derivative of sine is cosine. And then for this last guy, I have my 1/2, which stays. My derivative of natural log of 1 plus x is 1 over the stuff in the parentheses. And then it would be times the derivative of the stuff in the parentheses. But the derivative of 1 plus x is just 1. So now let me just rewrite this, and we'll have our answer. This is equal to 2 over x plus cosine over sine, well, that's cotangent, minus 1 over 2 times 1 plus x. And that is our answer. Now, could we have done the original problem without using the log properties? Yes, we could have, but it would have been, honestly, pretty torturous. And if you use just your chain rule with a quotient rule and a product rule and another chain rule, your answer would very likely not look exactly like this, but it would be equivalent to this answer. But when you have a logarithm with a whole bunch of stuff in it, sometimes it really helps to use the properties of logarithms, and it makes your differentiation much, much easier. In fact, it's so much easier that there's even a technique of differentiation called logarithmic differentiation. And we're going to talk about that right now. Logarithmic differentiation is used when you have a problem that has a lot of quotients and products and powers in it. So, to do logarithmic differentiation, you are going to take a natural logarithm of both sides of your equation. Then you are going to use implicit differentiation. And make sure that you solve for dy dx. Well, that's not too bad. We know all about implicit differentiation. We've learned how to do that already. So to do logarithmic differentiation, you basically just introduce a logarithm to the problem and then use our implicit differentiation that we already know. Let's do an example like this. We are going to differentiate the function y equals x squared times the cube root of 7x minus 14, all divided by 1 plus x squared to the fourth. And I'm going to use logarithmic differentiation to do this problem. Could we do this without logarithmic differentiation? Yeah, we could. If we did it without logarithmic differentiation, this would be a quotient rule with a product rule with a chain rule and another chain rule. And that's an awful lot of work. So we're going to use logarithmic differentiation. Logarithmic differentiation says you start by taking a natural log of both sides of the equation. So I'm taking a natural log of both sides. Like that. And then you're going to use your logarithm properties to rewrite this really complicated side as a sum and difference of logarithms. And I'm going to go ahead and just rewrite it in one step. You can take multiple steps to do that, but I know we've done quite a few problems with logarithms in our previous video, so we've had plenty of practice. After I break this completely out, it's going to be a 2 natural log of x plus a 1/3 natural log of 7x minus 14 minus 4 natural log of 1 plus x squared. So that's using all of my logarithm properties to rewrite that really complicated logarithm. And now we're going to use our implicit differentiation. So we are going to take the derivative of both sides of the equation. Derivative of natural log of y would be 1 over y. But remember, with implicit, you need to multiply by dy dx. On the right side, 2 times the derivative of natural log of x is 2 times 1 over x. For my next one, I have a 1/3 times 1 over the stuff in the parentheses times the derivative of the stuff in the parentheses. And same idea with that last guy. I'm going to have a minus 4 times a 1 over the stuff in the parentheses times the derivative of the stuff in the parentheses. And now let's rewrite this so it doesn't look quite as crazy. So we're going to have our 1 over y dy dx equals 2 over x. On here, notice I can cancel a 7 out. So I'm going to end up with a 1 over 3 times x minus 2. And for this guy, I can multiply that 4 and the 2x together to get a minus 8x over 1 plus x squared. And so that looks a little bit nicer than what we had before. Now we have to remember what it is we're actually doing on this problem. We were trying to find the derivative of that original function. So we want dy dx. To get dy dx, I just have to multiply both sides by y. And I get dy dx is equal to y times all of this other stuff that we had. And now we're not quite done. We really would like our derivative to only have numbers and x's in it because my original function was a function of x. So what I can do is I can replace this y with what y is equal to. I know what y is because they gave it to me at the very beginning of the problem. So I can substitute my original equation in for this y to get my final answer. I get that dy dx is equal to my y, which was x squared times the cube root of 7x minus 14 all over 1 plus x squared to the 4th. And all of that was my y, and it's going to be multiplied by all this stuff that I have in the parentheses. 2 over x plus 1 over 3 times x minus 2 minus 8x over a 1 plus x squared. And that is my final incredibly ugly answer. And it is a pretty incredibly ugly answer, but we got the answer way easier than it would have been using the quotient rule with a product rule and a couple chain rules. Don't believe me? Go back to the beginning of this problem where we had the problem written down and try it the other way. And it's going to get pretty ugly pretty fast. Can you do it that way? Yeah, absolutely. You just have to be very, very careful, and it's going to be very, very tedious. But using logarithmic differentiation can sometimes make your life a lot easier. All right. So far in this video, we have focused only on our logarithmic functions, but we're also supposed to discuss exponential functions and inverse trigonometric functions. So let's take some time to talk about our exponential functions. The derivative of e to the x will likely end up being your favorite derivative. The derivative of e to the x is itself. It doesn't matter how many derivatives you take, e to the x will give you another e to the x for the derivative. Slightly more complicated, the derivative of any other exponential function, b to the x, is itself times the natural log of b. Honestly though, most of the time in calculus we really only see the natural exponential function. So you just really need to remember derivative of e to the x is e to the x. Let's do some examples using exponential functions. So let's differentiate. And our first one's going to be y equals 2 to the x. Now we can use that formula that we just had for b to the x, and we would get y prime is equal to 2 to the x times natural log of 2. And then we'd be all set. You could also do this problem using some logarithmic differentiation, which then uses implicit differentiation. But you can also just memorize the formula. Part B, let's differentiate y equals e to the negative 2x. This is a chain rule problem. I know what the derivative of e to the x is, but this is e to something more than just x. So it's a chain rule. The outside function is e to something. Derivative of e to something is itself. And then I need to multiply by the derivative of the inside function, which is the derivative of the exponent, negative 2. So what I get for this derivative is negative 2 times e to the negative 2x. The chain rule with an exponential function like this, you end up getting itself times the derivative of the exponent. But again, this is just your chain rule, derivative of outside times derivative of inside. Let's do 2 more of these. Part C, differentiate y equals e to the x to the third. This is another chain rule. We have an exponential function and a chain rule. So the derivative is itself times the derivative of its exponent. E to the x to the third times 3x squared, which you can rewrite as 3x squared e to the x to the third. One last one, just for extra practice. Y equals e to the cosine of x. Another chain rule. Derivative of an exponential using a chain rule is itself times the derivative of its exponent. Derivative of cosine x is negative sine of x. So I can rewrite that as negative sine x times e to the cosine of x. And there we go. Not too bad. Exponential functions are actually very nice to take derivatives of because of the fact that the derivative of e to the x is itself. It makes it very nice. All right, what I have next for you is 6 different derivative rules. It's all the derivatives of our inverse trigonometric functions. Let me just write them all down. The derivative of sine inverse of x is 1 over a square root of 1 minus x squared. The derivative of cosine inverse of x is very similar. It's the same exact thing, except it's negative. So negative 1 over square root 1 minus x squared. The derivative of tangent inverse of x is 1 over 1 plus x squared. And I can tell you right now, this one's going to come up again in Calc 2 quite a bit. So it's a real good one to have memorized. The derivative of cotangent inverse is just like the derivative of tangent inverse, except it's negative. And then all I have left is the derivative of secant inverse and cosecant inverse, and they're the most complicated ones. The derivative of secant inverse is 1 over the absolute value of x times the square root of x squared minus 1. And the derivative of the inverse cosecant is very similar, it just happens to be negative. So negative 1 over absolute value x, square root of x squared minus 1. So to finish this video off, we're going to do 2 examples that involve inverse trig derivatives, and they're also going to be chain rule problems. Those 6 inverse trig derivatives, I would suggest that you add those to the list in your head of things that are memorized, because when they come up, it's very good to know them already because they're kind of tricky to derive on their own. So I would suggest you have those memorized, as well as the derivative of just your 6 regular trig functions, derivative of e to the x, derivative of natural log of x, and then just know all of your rules and you'll be completely set. So an example, let's differentiate. Our first one is going to be y equals sine inverse of x to the third. So this is going to be a chain rule problem. We're going to have to do the derivative of the outside function, that's the derivative of the inverse sine, times the derivative of the inside function. So first we have to start with that outside function. The derivative of an inverse sine of x was 1 over the square root of 1 minus x squared. So I'm going to do the same exact thing, the same formula, except instead of where I had an x, I'm now going to have x to the third. So I get 1 over the square root of 1 minus x to the third squared. That is just the formula for the derivative of an inverse sine, but I replaced my x with an x to the third. Then I have to multiply by the derivative of the inside function, which is a 3x squared. So simplifying just a little bit, I'll have 3x squared on the top, and in this square root, I have 1 minus x to the 6th. Part B, differentiate y equals secant inverse of e to the x. This is going to be a chain rule again. I have to have the derivative of secant inverse with every single x replaced with e to the x, and then times the derivative of e to the x. So my derivative of secant inverse, that was one of those complicated ones. It was 1 over the absolute value of x times the square root of x squared minus 1. But since I don't have a secant inverse of x, I have a secant inverse of e to the x. I have to replace all of the x's in that formula with e to the x. Then I just have to multiply by the derivative of the inside function. Derivative of e to the x is itself. And now we can simplify a little bit. First, I'm going to have e to the x on the top. The absolute value of e to the x is e to the x. Remember, our exponential function was always positive. Then underneath the square root, e to the x squared is e to the 2x, and I have a minus 1. So then you can see my e to the x's will cancel out, and the simplified version of this derivative is y prime equals 1 over a square root of e to the 2x minus 1. And there we go. So that was a lot of new rules in this video, a lot of memorizing that you're going to need to do, but just lots of practice using all of our derivative rules all together. Pretty soon we're going to be ready to use more applications of the derivative, related rates problems, eventually graphing, optimization problems, all sorts of cool stuff coming up pretty soon. So take your time, make sure you memorize the rules that you need to have memorized and get lots of practice in so you can tackle the hard problems that are coming up fairly soon. If you have any questions, you can drop them down below. If you're a current student of mine, you can also email or come to my office hours to ask your questions, and I'd be more than happy to help you. I'll see you in our next video.